Well, welcome everyone to our 12th CRM Camp seminar of the series. Today, it's my pleasure to have Isaia Nisoli from Brazil, Universidade Federal de Rio de Janeiro. So Isaia Nisoli was born in Bergamo, Italy, as he was saying when we were chatting. He did his PhD at the University of Pisa under the direction of Professor Marco Abate in holomorphic dynamics. And actually during his PhD, started to work with other professors, including Stefano Galatolo, who's present with us. And he was working with him on computational ergodic theory. He got his PhD, he finished his PhD in 2011, and then he moved to Brazil, where he is actually right now. We could see beautiful background. And there he worked as a postdoc with Professor Maria Jose Pacifico. And since 2013, he has been an assistant prof at Federal University of Rio de Janeiro. And his research interests include computational ergodic theory, non-uniformly hyperbolic dynamics, random dynamical systems, and noise-induced data. And this morning, it is my pleasure to introduce him, and he will be giving a talk about the proof of noise-induced order in the BZ map and some remarks on the phenomenon. Please, Isaia.
Okay, so I will start with a really nice part that is this movie is not made by me, but it's about the Belousov-Zhabotinsky reaction. And the Belousov-Zhabotinsky reaction is a chemical reaction that brought big it changed in some sense the way chemists look at chemistry, because it's the first example of non-equilibrium thermodynamics. So it's a chemical oscillator, and it became it's really beautiful. It also has this really nice pattern forming, and then there was a lot of interest in about this chemical reaction in the 70s, with a lot of applied mathematicians studying it. And today we will study, I will show how we prove a conjecture that was made by some applied mathematicians in the 1980 about the fact about noise-induced order. Okay, so just 1 second, it's okay. Presentation. So these are the two names of the reaction, are Belousov and Zhabotinsky. There is a kind of terrible story about this. So Belousov left just before the First World War. He left Russia, went to Switzerland, where he took his degree in chemistry, went back after the Russian Revolution to collaborate to the effort for to the socialist effort after the revolution. And he was studying non-organic analogs of the Krebs respiration process, and he discovered this reaction called the Belousov-Zhabotinsky, the Belousov reaction. And he tried to publish it in one journal, other journal. Since it was so groundbreaking research, and it was so against what was common knowledge for chemistry at the time, he had really strong difficulties of publishing that. He ended up publishing it in a small, non-peer-reviewed predatory journal of the time. And then arrived Anatol Zhabotinsky, and the chief investigator of Belousov gave to this PhD student the thesis topic of studying this oscillatory reaction, and then it became known to the world as the Belousov-Zhabotinsky reaction. And there are these chemical oscillators, and if you take data and you measure data from the generated by this reaction, you can see some, you can analyze the time series, and you can see positive Lyapunov exponents. If you excitate the reaction, then you have this pattern developing. So it's really interesting from a chemistry point of view, and it also became really interesting from a mathematical point of view. So we have this a plot of the next potential of the minimum of the Brom ion in function on the nth one, and this is one of the curves that were studied for one of the models, one of the interesting maps that were associated to the Belousov-Zhabotinsky reaction. And Matsumoto and Tsuda, in 1980, they interpolated this curve, the curve above, and studied studied a random dynamical system associated to a deterministic dynamic, which is an interpolation of this curve. So this is the Matsumoto-Tsuda map, and what we mean by a random dynamical system means we take an iteration of the model, we add a random noise, and we take an iteration of this new value with the added noise, we iterate again, we add a noise, etc., etc., etc. And what happened in their seminal paper in 1980 is that they showed that computing Birkhoff averages they compute really long random orbits of this system. They compute the Lyapunov exponent, and they vary the size of the noise. So you permit that the noise before the jump is small. You can have only small jumps, and when you permit really big jumps, what happens is that when the jumps are small, the Lyapunov exponents along the orbit is positive, and when the jumps are big, the Lyapunov exponent becomes negative. And this is what they called noise-induced order. Okay, and this was done by numerical experiments, and it's a paper that was of really huge interest for the applied mathematical community and for the physical community in the 80s. It has more than 400 citations. It's a really interesting problem, but up to now, this was only proved and conjectured by numerical experiments. Okay, and one of the reasons why it's so difficult to say something about this BZ map is that the BZ map is ugly. Okay, it's really ugly. It has it has some really ugly points. So it has a point where the derivative is 0. So you have a coexistence of contraction, and so it cannot be uniformly hyperbolic. There is a point where the derivative is infinite. Okay, the second derivative is has a jump discontinuity at 0.3. So you have this coexistence of infinite derivative, 0 derivative. It has a really huge contracting part. If I don't know if you can see my pointer. So you have this expanding part, you have this huge contracting part, you have this point where the derivative is 0, you have this point where the derivative is infinite. So it's really difficult to understand what happens with this map. Okay, non-uniformly hyperbolic dynamics is a really difficult topic, and usually treated by introducing induction schemes, and it's really technical. And essentially, the current results, they may be used to prove something about this map, but in general, treating the BZ map is really difficult. And our objective today is to show the transition. We will show that for small noise, we have a positive Lyapunov exponent, and for a big noise, we have a negative Lyapunov exponent. And what we want to do is also try to understand what's going on. So why do we have this kind of transition? And our strategy consists of the following. We will develop an approximation schemes that permits us to approximate the stationary measure of a random dynamical system in L1. This approximation scheme is really general, so it can be used essentially for most systems with random additive noise. So essentially, the only thing that we need is that the noise is in BV. Okay, we prove that the random dynamical system is ergodic with respect to this stationary measure, and then we will compute the Lyapunov exponent of the stationary measure with respect to different noise amplitudes. Okay, so our idea is that we take a noise of small size, we approximate the stationary density, we approximate the Lyapunov exponent. We take a noise with big size, we approximate the stationary density, we compute the Lyapunov exponent. If one is positive and the other one is negative, we have proved our theorem. So this is a theorem that in some sense is a theorem a posteriori. So if our computations end, we have proved our theorem. We prove our theorem. Okay, and so the approach to approximate the stationary measure is to discretize the operator. To discretize it rigorously, we are going to use interval arithmetics, so rigorous Newton methods. We are currently developing now a Julia package for the approximation of invariant measures and stationary measures that is based on the work by Sanders with their validating numerics Julia package. So in the future, we're going to, it's already available, so you can, it's not so fun to play with because there are not so many things. It's not still capable of many things, but with time we are adding capabilities. And why I say we have to discretize the operator? In some sense, we could think, okay, we take a really long, we compute a really long orbit and try to compute the Lyapunov exponent, but it depends really on how fast is the Lyapunov exponent converging to the average. So there are many issues involved with this. And also one of the issues is that when we represent a dynamic in a finite floating point arithmetics, what happens is that this dynamic becomes a dynamic on a finite set. And so in general, we don't see generic behavior, or it's really difficult to prove that this is generic behavior, okay? So what we do is that we are going to approximate our dynamical system, okay, or our random dynamical system by a Markov chain, okay? So we will divide our interval into pieces of the same size, and we will compute essentially what's the probability if you are in one of these intervals to get into the other interval, okay? This Markov chain, under some assumptions, okay, on the underlying dynamic and on the underlying noise, is irreducible and aperiodic. And so we have Perron-Frobenius theorem, we have a unique fixed point. This Markov chain is represented by an n-per-n matrix, so we can try to use this Markov chain that we have computed rigorously to compute an approximation of our stationary measure. Okay. Now there are some issues about Ulam. First of all, we don't know if this Markov chain, if the behavior of this Markov chain effectively mimics or approximates the behavior of the system. Okay. This, in some sense, depends on the fact that that there is not too much microscopic behavior. So in some sense, there is at some point you have a size at the resolution at which you are seeing the behavior of the system. Okay, this is connected to uniform hyperbolicity. So what could happen is that in some non-uniformly hyperbolic dynamical system, you get some really small, that at some point you make a partition so small that you only see that you have an absorbing state when you make a really small partition, and maybe, and so it's really complicated to say, or at least it's really complicated to say when the Ulam, there are some theorems that tell us when the Ulam approximation mimics the behavior of the system. Another question is if there are better partitions. So if we take a Markov partition for the map, this is better than the homogeneous partition. And the third question is, okay, we have computed our stationary measure, but does this have any connection with the stationary measure of the system? Okay, and so I would like to move now and just speak a moment about the transfer operator. And the transfer operator is an operator on the space of measures, okay, that extends the dynamic. So you can see it easily if you take the transfer operator and apply it to a Dirac delta, you get the Dirac delta on the image of the point. Okay, so what happens is if you take a a convex combination of Dirac deltas, what happens is that the transfer operators moves them on the image of the points where the deltas are. And so you can understand that this transfer operator is, as its name says, it's moving around densities, it's moving around measure, okay? And for a random dynamical system, we are going to study something which is called the annealed transfer operator. And the idea is that, okay, we move our point forward in time, okay, one step, but then we want to average over all possible noises, okay? And this is essentially embodied by the fact that we study this operator, where we apply the transfer operator, okay? And when we take, and then we take the convolution, so the transfer operator is moving around measure, and then we convolute these measures with respect to the noise. So what happens is that if you think about a Dirac delta, so you're moving this Dirac delta to its image, and then you're spreading it all around using the noise, okay? So, and why this operator is really good for us, and the fact that the convolution is regularizing. So, so it's making the densities. It's making the density an object which is in a good function space. Okay. The idea is that when we split up the partition, we can take a function which is in L1, okay, and project it by taking its average over each element of the partition. So we get a piecewise constant function, which is constant on each element of the partition. And in some sense, what happens is that if we take this projection and compose our operator with this projection, what we are going to see is a finite rank operator. It's just a matrix, okay? And luckily, this matrix is exactly our approximation by a Markov chain. Okay, so taking a partition and averaging a function over each element of this partition, okay, and getting therefore a piecewise constant function, and composing this projection with our transfer operator gives us exactly this intuitive idea that we had of approximating our dynamical system by a Markov chain. Okay, and okay, when we work with the annealed transfer operator, we have also to approximate the action of the noise. So what we do is that we have a Markov chain that comes from the dynamic, and then we have a Markov chain that is given by the discretization of the noise, and we compose them. And this is essentially our our discretized operator. Now, why does this process work? Okay, or better, when does this process work? And the reason why we can approximate our system by Markov chain is the fact that our dynamical system, our random dynamical system, it preserves a space which is more regular than L1. So there is this notion of variation, and variation is it's defined. So we take the soup over all possible partitions of the difference of the function at the endpoints of the partition, sum them, and if variation is bounded, okay, if this variation is bounded, then we say that a function is of bounded variation. And what happens is that if we use the Ulam projection on a function of bounded variation, the projection of the functions and the functions have an error that goes as the size of our partition. Okay, so if we can prove that our system is preserving functions of bounded variation, what we expect is that in some sense this function may be visible by our discretization. Okay. So when in other cases, when we can approximate the invariant measure for deterministic systems, we have a so-called Lazotta-York inequality that proves that our system is preserving bounded variation. And so in some sense, we call an operator that is preserving bounded variation a regularizing operator, okay? And in our case, the regularizing property of the transfer operator, of the anneal transfer operator, it comes trivially from the convolution property. Okay, so since we are convoluting with a uniform noise, okay, which is a function of bounded variation, then any function is going to be their variation is going to be bounded by the variation of the noise. Okay. And so since this operator is regularizing, okay, since it preserves BV, what happens is that we can bound explicitly the distance between the iterations of the original operator, okay, and the iterations of our discretized operator. Okay, and since we can bound this distance, and since if both of the operators have a unique fixed point, we can bound the distance between these fixed points. Okay, so this is a theorem, and these are the fixed points of the operator and of the discretized operator. So we can bound this distance in L1 once we know this CK. Okay, so these CKs, they are if you're used to Markov chain terminology, essentially we are looking at how fast the discretized Markov chain is mixing. So we take the space of average zero measures, and we make the computer compute. Okay, we have a matrix, and we make the computer compute the norm of powers of this matrix when restricted to the space of average zero measures. This is telling us how fast the discretized system is mixing. Okay, this is sometimes it's called Markov chain mixing times, etc., etc., etc. So there's these results on the fact that you have many iterations where nothing happens, and then you have a cutoff, and you start seeing contraction. Okay, so this is, I probably you remember that at the talk by Caroline, she told, okay, here I have a priori estimate about the spectral radius of my operator, and while Galato, Nisoli, and so on, they use an a posteriori estimate. So what happens is that this is our a posteriori estimate. This is something, so we have an operator, we discretize it, and then we just say to the computer, okay, now iterate this operator 80 times, okay? If at some points we see contraction, then our argument works, okay? And we can prove, and we can find this. We can use this estimate. If we don't see contraction, we cannot prove that the system is not mixing, but this is not, so not seeing contraction in a short time is not a proof that the system is not mixing. But if we see contraction, we have a proof that the system is mixing. Okay. Indeed, we have this result that tells us not only if you see that your discretized system is mixing, then the original operator is mixing. Okay. And this is a really strong result, okay? And this is what we use to prove ergodicity of our stationary measures, okay? So essentially, the idea is we have an operator, we discretize it, we compute powers of this operator in a rigorous way with rigorous error bounds. If one of these powers contracts the space of average zero measure, then it kickstarts all our argument, and we can prove that and then we can approximate the stationary measure, and then we can prove that the stationary measure is ergodic, and so on and so on. Okay? So these are approximations of the stationary density for the Wiese map, and this is for a small noise size, and this is for a big noise size. Okay, and what happens is that Matsumoto and Tsuda, when they studied their model, they choose a parameter so that the critical value of the map would land on a repelling fixed point in 3 steps, and you can see this by looking at the stationary measure for the stationary measure for small noise. You can see that you have this bump here, and this is the repelling fixed point of the original map. Okay, it's a bump around the repelling fixed point of the original map, and here you can see that the orbits are not spending so much time anymore around the fixed point of the repelling fixed point. Okay. And this is one of the, so what happens is that the noise is making our random dynamical system move in a much more uniform way inside the interval. Okay, so in a non-uniformly hyperbolic setting, you have positive Lyapunov exponent because you're spending, with respect to the invariant measure, you're spending more, you visit more frequently the part of the system where you have expansion than the part of the system where you have contraction. Okay, so when you add noise, what happens, since the noise is moving you uniformly inside the system, so you end up spending more time in the part where you have a bigger Lebesgue measure. Okay, so since we had this huge piece where we had the contracting part, then the noise is throwing us inside the contracting part with really high probability. Okay, so this breaks up the so instead of seeing in average expansion, since now you're being thrown inside the contracting part with a high probability, then we see in average contraction. Okay, I just want to make a remark on the fact that why we use Ulam and we don't use spectral methods. And in general, spectral methods, they converge really fast, they converge exponentially when the dynamics, or in this case, the noise, are analytic, or are in some sense analytic, okay? When you have something which is in BV, or when you have a system that only preserves BV, like in our case with the uniform noise, we know that the Fourier series converge slowly for BV functions. They converge as 1 over k, where k is the number of terms in the Fourier series. Okay, and so essentially, to approximate as well as we are doing the stationary measure, we would need a matrix of the same size. Okay, because Ulam there goes to 0 as 1 over k, and the spectral methods there go to 0 as 1 over k. But the huge issue is that when you use spectral methods, the matrix that you're obtaining is non-sparse, while our matrices are sparse, because when you essentially you're counting the number of intervals that have non-empty intersection with your starting interval. So you send an interval into the future, okay, and so you have that at most it's going to have the number of intersections that you're going to have is at most is bounded by the derivative, by over and above, by the derivative inside the interval. Okay, so we know that in our method we get a sparse matrix, and since we have a sparse matrix, then we can iterate this sparse matrix and prove this contraction. Okay, and this is the graph of the Lyapunov exponents for the Belozov-Zhabotinsky map, for the Bezier map, and you can see that here we have for a small noise we have positive Lyapunov exponent, and as the noise grows, we get a negative Lyapunov exponent. So, and then down. Okay, and the paper, if you look at the paper, so there are many questions that can be asked about the paper, and one of the questions that was asked was, okay, but so you said that for the Matsumoto and Tsuda, they choose a specific value of the constant b, okay, so that we had a repelling fixed point. So how sensitive is your proof with respect to these constants in the Bezier map? And what happens is that we can prove once we can prove mixing of the original system, we can prove that the Lyapunov exponent is Lipschitz with respect to the parameter b, which is this parameter that sends the map, the critical value inside the aperiodic repelling point. It's Lipschitz with respect to the other parameter c, and it's a log a Lipschitz with respect to the other parameter a. And our techniques permits us to compute explicitly these Lipschitz constants. This is so everything. So our method gives us explicit Lipschitz constant, gives us explicit estimates on the Lyapunov exponent, gives us the explicit form of the stationary measure. Okay. And now I would like to comment about some further developments that I have in this direction. And essentially, I have this theorem, and this theorem is essentially it stems from our research on noise-induced order. And what this theorem says is that if you have a dynamical system which has positive Lyapunov exponent with no noise, and which has a positive and which has a unique absolutely continuous invariant measure, and you have this stochastic stability. So when when the noise size goes to 0, the Lyapunov exponent of the noisy system goes to the Lyapunov exponent of the original system. And this is a more technical condition. So if you add a small noise, then you see mixing, okay? But if the integral of the system with respect to, of the logarithm of the derivative of the system with respect to Lebesgue is smaller than 0, then we have noise induced order. So this map, the busy map, that seems really pathological, indeed it is not alone. So there are many examples that have this noise-induced property. And the most simple example of everyone, and this is just if we take unimodal maps, okay, unimodal maps, and instead of having a quadratic critical point here, where the derivative goes to 0 quadratically, if we take alpha bigger 2.678358, this is a constant that I can compute, then from this parameter over, then we have noise-induced order. And the structure of this, so we have a lot of noise. Indeed, this proves that we have at least one transition, but this is not rigorous. This is not a rigorous graph. But what happens is that this on the y direction you have alpha, so it's the order at which you have this vanishing, and in this direction you have the size of the noise, and this is the 0. So you have this curve, which is the 0 level curve for the Lyapunov exponent. And you can see that we have a huge zoo and variety of different noise-induced behavior. It can be. So I proved that you have at least one transition, but you can see that here we have a 1, 2, if you take 5 as an example, you have 1, 2, 3 transition, and you can have tangencies to the level lines. And so the behavior of dynamical system with additive noise is something that is really interesting, and I think that with time is going to become a really interesting topic. Okay, and so this is essentially what I wanted to ask you, to tell you. Okay, so thank you for your attention. This is my cat. She's not really happy.
Thank you.
I went really fast.
It's okay. We have time for questions then. So thank you very much, Isaia. Are there any questions or comments?
Yeah, I have a question. Can I ask a question, please?
Yes.
Oh, okay. Yeah. So can you go back to the theorem of the contraction theorem, where you have you estimate, you measure the difference between the U and the U delta, right?
Yes.
Yeah, that's right. The previous one, I think it's
okay.
like we have all the CKs. Yeah, that one.
Yeah.
So what do the CKs depend on?
What do the CK depend on? Okay, so this is so they're essentially they are a measure of how fast the system is mixing. Okay, but so in principle you could try to use some of these techniques that come from a Markov chain mixing time analysis and so on. But what we did is taking a brute force approach. Okay, we don't care about the structure of the Markov chain. We just run it until we see contraction. Okay, so in principle, you could try so an analysis. So first of all, I have to say one thing that probably it's not really clear was not really clear, but the size of the Markov chains that we use to study our problem is of the order of 10 million states or 12. So it's something of the order of million of states. Okay, to get these approximations, especially the one for small noise, we need Markov chains that have million of states. Okay, so we don't do any analysis on the graph structure of the Markov chain to get get an a priori estimate. It's an a posteriori estimate that is done poorly computationally. Does this answer your question?
Yeah, if I can be a little more specific, I was wondering if they depend on the map or they depend on the kind of partition, because I seem to understand you use all a uniform discretization, right? So does it depend on whether you use uniform discretization or whether you use a Markov partition or some other kind?
Okay, so these constants, they clearly depend on the map, okay? And they clearly depend on the noise size. Okay, this constant is different for small noise size and for big noise size. Okay, and this depends also on the partition. Okay, this depends also on the partition. And in principle, if you add a Markov partition, you could probably get better estimates for this. Okay, but our method uses a homogeneous partition, and it works for all maps and for all noise that are in BV. Okay, so in principle, these constants depend on the noise and depend on the map, but if the system is mixing at some point, then if you had a perfect computer that could compute rigorously the bound on these norms for a huge case, because you have to be careful, because at some point, if you iterate too much the matrix, you could have an accumulation of numerical errors, so you don't see it, and you don't see anymore, you don't get any useful estimate anymore. Then you could, in principle, see these for any map. Okay, so these constants, they depend on the map, depend on the noise size, and they have to be computed case by case.
I have a question, actually. Hi, ciao, Isaia.
Ciao.
So my question is, we probably already talked about this, but somehow I can never quite remember. So when you say that the dynamics for large noise has negative Lyapunov exponent, does that mean that almost every realization has negative Lyapunov exponent, or is it an average of the Lyapunov exponents for each realization?
So what happens is that with the probability 1, with respect to all the noises, you see this Lyapunov exponent for an orbit.
Right, so almost every realization actually has negative Lyapunov exponent.
Yes.
So what do you actually see for one of those realizations? What does the dynamics look like with the negative Lyapunov exponent?
So what happens is that there exists a Bayesian theory for random dynamical systems. So if you have a negative Lyapunov exponent, you have local stable manifolds. Okay. So yeah. So what happens is that the orbit for each point of the so you have a local stable manifold. So you see essentially that the orbits, that nearby points are attracted to the orbit.
That's right, but so does every orbit have the same statistics? I mean, so if you computed the Dirac averages of the orbit, do they all have the same limiting behavior?
So indeed, there is a paper by Alex Blumenthal and Laizan, which is relatively recent, that shows that in the case of random dynamical system, the empirical measures are converging to the SRB measure. Okay. So in some sense, what happens is exactly, and also there is also a paper by Shen where it shows that essentially all the empirical measures have the stationary measure as weak star limit. Does this answer your question?
Okay, thank you. Yes, thank you.
Are there any other questions or comments?
I have one more question, if I may.
Sure, Domenico. Yeah, go on.
Yeah, thank you. So my question is, so speaking of the mechanism of noise-induced order, right? You said that, so when the noise is strong enough, it kind of throws you into the contracting regions, right?
Yes.
So is this, can you explain this intuitively, or it just comes out of the calculations, or you prove it? Well, what is the mechanism? I didn't quite understand.
So probably I don't know, probably you have seen at some point the stationary density, the invariant density for the quadratic map. Okay, so these are, so you can take, if you take the quadratic map, I will open the whiteboard. Okay, so if you take the full branch quadratic map for x times x minus 1, so you have that, I'm sorry that it's ugly, but I will try to draw. So what happens is that you see something like this, okay? So what is telling you this density is that you're spending a lot of time here, okay? You're spending a lot of time here, but you're not spending so much time here in the middle, okay? Because the density by Birkhoff-Ergodic theorem is telling you with which frequency you're visiting each part of the system, okay? So now in these models, like these 2x alpha minus 1, okay? What happens is exactly the same. I put them on minus 1, 1 because you get a better, it's easier to write the map, but indeed you can just transform them into something else. I'm sorry that so this is the density, okay? So what happens is that, okay, so if you're just moving with the dynamic, you're spending a lot of time here and a lot of time here. Now, suppose that you jump here, okay, under the dynamic action, and then you add noise, okay? You add your noise, and so if your noise is small, you're going to do a small jump, and okay, you're going to stay inside this contracting part, this expanding part. But if the noise is big, even if the image of your point was inside the expanding part, you may jump inside this contracting part. Okay, this part is contracting because if you look at the derivative, this is the map, this is the dynamic, and here you have 0 of the derivative, so you will probably have a big part. And so since the derivative is continuous, here you have a point where the derivative is 1. Here you have the point where the derivative is 1. Inside here, the derivative, you see contraction. So the logarithm of the derivative is smaller than 0. And here outside, the logarithm of the derivative is bigger than 0. So you can think that if you add a lot of noise, if your noise is huge, what you're going to see is that you make a jump, and then you take a jump uniformly inside the interval. Okay, this is the main idea. You take a jump, you arrive in a point, and then you move uniformly inside the interval. So what happens? If the contracting part is much wider with respect to Lebesgue measure than the expanding part, since you're making a jump that moves you uniformly inside the interval, then you will end up with a much higher probability inside the contracting part. So your point ends up there. So nearby points end up there under the action of the same noise. And so now you have contraction, and then you can move around, but essentially your dynamic may move you inside against, again, the contracting, the expanding part, but then you jump uniformly. And so you have a really huge probability of getting inside the contracting part, okay? And so essentially what you see is a kind of it's a kind of random, uniform, random walk inside the interval, but that then has some contraction or expansion depending on where you are inside the interval. So nearby orbits are approximated or spread out depending on where you land with your random walk, essentially. Uniform random walk. Did I make it more clear?
Okay, thank you. So this can be actually proven more rigorously. Is there a proof for this?
Yes, this is essentially this is my preprint. If you now I'm rewriting this. So the preprint is kind of I'm rewriting the preprint, but I have a theorem, and the theorem is exactly like this. So this is what happens when you have this uniform random walk. So when you have a uniform random walk, what you're seeing is essentially the average of the logarithm of the derivative with respect to Lebesgue, okay? And if the original map has positive Lyapunov exponent, it means that that with respect to its invariant measure, she's staying more time in the expanding part instead of in the contracting part. And then what is a really difficult part, and in which I rely on strong theorems by Shen or Baladier and Viana, etc., are these R1 and R2 hypotheses that are something that is called the stochastic stability of the original map, and that depend on something that is called stochastic stability of the original map. This essentially means that the system with noise the behavior of the system with noise goes to the behavior of the system without noise when the noise size goes to 0. Okay, so this is a theorem. This is my last work. Yeah.
Okay, very good. Other questions or comments? Actually, I have one regarding the very beginning of your talk, when you talk briefly about how to go from this chemical reaction to the actual map. There's something I did not really get on how to get that discrete dynamical system out of this complicated, beautiful phenomenon.
Reaction. Yeah, it's this is really complicated. So
but do you have like a rough explanation?
So what happens? So so they got this dynamical system from this map, and this map is something that they got from measurements. So they took the chemical reaction, they put it into a reactor, okay? So it's a really confined space, and then they just measured these. They measured the time series of the potential of this ion, of this bromine ion, and they got this curve. So this is essentially this is the Poincaré. So they took a minima of this brom potential, and they plotted the next with respect to the former minima. Okay, so in some sense they want to see if there was some connection between these minimas with the time series. They got this nice curve, and then arrived this, and then Matsumoto and Tsuda, they took this curve and interpolated it, and that's how they built up our dynamical system. What our result means for the original chemical reaction, I don't know. Okay, I don't really know if there are some if our result has some consequences. They could prove that inside the original chemical reaction there is noise-induced order. So they made experiments where they proved they took the chemical reaction, added noise by adding some I think there was some turbulence added by a piston, and they checked that with the small noise, the time series generated by the measurement had positive Lyapunov exponent, while with huge noise it had the negative Lyapunov exponent. But I don't have any more in-depth explanation about the phenomena.
Mm-hmm. Okay, thank you. Other questions? Actually, I had maybe one last one. So when you say it's computer assisted proof. So you say basically, you know, we have to iterate this map for long enough, and then at some point, if an inequality is satisfied, then you have what you want. So in terms of in practice, you say that you use Julia, and you discretize.
So we are now moving to Julia, but before this essentially was done mostly in C++, in Python and C++ by using OpenCL to do the iteration of the matrix. Because,
okay.
Okay, yeah.
Okay, I see. And then the actual discretization for the operator, maybe you mentioned that, but I think I got lost. So you know, you have this operator, and you say you discretize it, and then you iterate it. So which discretization again did you use? What kind of?
So essentially, we split up the interval into equal pieces,
yeah.
And then we compute. So we take the preimage of the interval, and we compute how much of the measure of the so essentially what we compute with the rigorous method is this guy. So we compute the length of the intersection of the preimage of the interval with the interval, and this gives us the conditional probability of getting from interval J into interval I under the action of the dynamics.
Okay, the Ulam approximation, I see. So if say the method of Caroline Wormel, it would have been, say, to take that operator and then to discretize it in Chebyshev, whereas you're using this approximation for your.
Yes.
Okay,
exactly.
okay. I see, yes, okay, thank you very much. All right, so maybe I'll ask one last time. Are there any more questions or comments? Okay, well, if not, it was a real pleasure to have Isaia to give us a talk today. I thank you very much once again. And